Hey everybody, I'm Bill Kinney and this is my Abstract Algebra Exam 1 Review Problems and Solutions video. If you're looking for lectures about abstract algebra, I would encourage you to check out my playlist in the description below. In this exam, we go through problems that are about the basics of group theory. If you happen to have Gallien's book, it covers chapters 0 through 6. That's basics number theory, equivalence relations, functions, the definition of a group, subgroups, subgroup test, order of an element, order of a group, cyclic groups, permutation groups, and finally isomorphisms. The types of problems that we work through here include definitions, true-false questions, calculations, and finally some proofs. We'll start with some definitions about number theory. Let A and B be elements of Z. Z is the set of integers. We need to define what it means for A to divide B. To be a divisor of B is another way to say that. Divide evenly into B. In other words, when we take B and divide it by A, the intuition is B divided by A, if we write it as a fraction, is an element of Z as well. That is essentially the definition, but we want to avoid the fraction here, actually. That's the idea. Instead, what we want to do is we want to think of it in terms of multiplication. A dividing B, written like this, A with a vertical line, B means A divide B, means there's some other integer, m, say, where B equals m times A. There exists, a backwards E means there exists, some integer m is in the set Z of integers, such that, ST is my abbreviation for such that, B equals m times A. Okay? That means A divides B. A is a divisor of B. A divides evenly into B. All those mean the same thing. You could also say A is a factor of B, is another way to say that. On to the next fact here. We want to state Euclid's lemma. Okay, so this is something that needs to be memorized. It's a fundamental fact from number theory. We start by letting A, B, and P be integers. They are elements of Z. And suppose that P is prime. Okay, this applies in the situation where the P is going to be prime. Then if P divides the product A times B, the conclusion is that P divides either A or B or both. But you only need to say P divides A or P divides B. This is an inclusive or, it could be both. This should make some intuitive sense. If P divides the product of two integers, that means it's a prime factor of that product. You know A and B have prime factorizations by the fundamental theorem of arithmetic. P has got to be one of the factors either of A or B or both. Thought of another way, if P does not divide A and does not divide B, in other words, P is not in the prime factorizations of either A or B, it can't possibly be in the prime factorization of A times B. It is important that P is prime here. For example, if P is not prime, the conclusion can fail. Notice that 6 divides 3 times 4, because 3 times 4 is 12, and 6 divides 12, but 6 does not divide 3, and 6 does not divide 4. So that illustrates the assumption that P is prime is essential to making this if-then statement correct. Okay? That's just a side comment there. Next problem. Define what it means for two integers to be relatively prime. One way to define it is to relate to the fundamental theorem of arithmetic and say that A and B have no prime factor in common. What we usually do, however, in abstract algebra, is we say A and B that are integers are relatively prime if their greatest common divisor, or greatest common factor if you prefer, is equal to 1. That's typically written GCD, greatest common divisor, of A and B. Again, you could also call it GCF for greatest common factor. It means the same thing, equals 1. That's the definition of relatively prime. It also does mean they have no prime factors in common. It doesn't mean they are prime, they just have no prime factors in common. They are relatively prime with each other. For example, 6 is 2 times 3, it's got 2 and 3 as prime factors. 35 has got prime factors of 5 and 7. 6 and 35 are relatively prime. They have no common factors. And you could also say the greatest common divisor of 6 and 35 is 1. 1 is the biggest positive integer that divides evenly into both 6 and 35. Problem 4 is a fundamental problem. Define what it means for a non-empty set G to be a group in group theory, okay? All right, so this is definitely something that people who are learning about group theory should know deeply. They should have memorized. You can write it in various kinds of ways. I'm going to go ahead and write it this way. This means there is a binary operation. And when I say binary operation, I'm consistent with Galilean here in saying that the binary operation by definition is closed. You could write it like this. It sends the ordered pair A comma B, where both these things are in elements, they're elements of G, and maps it to AB, where when we write a symbol like this in group theory, we're thinking of this as A times B. You could put a dot between those, but it's traditional not to bother, as common in math when you've got two symbols that represent two numbers, say, and you put them next to each other. It's assumed that you're multiplying them. So this is also in G. This really is closure here. Some textbooks separate closure out as a separate property that you're saying the binary operation has to satisfy, but I'm essentially assuming binary operations satisfy closure. That is consistent with Galilean's book, such that 3 other properties must hold. The first other property is that this binary operation is associative. AB, or A times B, in parentheses, times C, equals A times, in parentheses, B times C. In other words, if you first take A times B, get a result, and then multiply by C on the right, say, you get the same result as if you do this, meaning multiply B times C first, and then multiply by A on the left. You can switch where the parentheses are, which ultimately means you actually don't need parentheses at all. This is true for all A, B, C in the group. This is the associative property. Associativity. Second property is there needs to be some identity element. There needs to be something in G such that when you perform the binary operation with an arbitrary element of G, call it A, you get that element A back. There exists an identity element, sometimes written as a 1, but usually in group theory written as an E. That's not the number E. It's not 2.71828, blah, blah, blah. It's an element E of the group. E is German shorthand for Einheit, I believe, such that A times E equals E times A equals A for all A in G. I'm going ahead and saying both of these things equal A. That doesn't mean in general G is commutative. A times B is not necessarily equal to B times A for all A and B in G. However, with this identity element E, it does commute with any other element, and it equals that other element, no matter what that other element is. This means there exists. This means for all. This is called the existential quantifier. This is called the universal quantifier. They are important to include. And the third property is that each element has a multiplicative inverse. For each A and G, for all A and G, there exists some other element, which initially we could call, say, B, but I'm going to go ahead and use the inverse symbol right away. There exists a symbol, A inverse, an element of G. Again, you could call it something else, but this is suggestive, such that A times A inverse equals A inverse times A equals the identity element. Okay? That's the definition of a group. You might wonder, is the identity element unique? And for a given element, is its inverse unique? The answer is yes, but it's not part of the definition. It would be an example of something that you should try to prove. Okay? Problem 5. Let G be a group. Give a definition of what's called the center Z of G of G. Okay, so again, something to just know, to have memorized. Z of G, by definition, is the set of all elements of G that commute with every other element of G. And to tell you the truth, with my students, if you want to write that out in words, I'm actually fine with that. This is the set of all elements of G which commute with every other element of G. That's kind of wordy, but it's worthwhile to try to make sure you think about these concepts in terms of words, in terms of descriptions. The set of all elements of G, or in G, which commute, A times B equals B times A, with every other element of G. And yeah, commutativity is not part of the definition of a group. When a group is commutative, when every element commutes with every other element, as it will be the case if Z of G equals G, then we say the group is commutative, but it's actually more common to say it's Abelian in honor of Abel, A-B-E-L. In terms of set builder notation, it's a little quicker to write. You could write this as the set or collection of all elements, call them A, in capital G, such that this vertical line means such that the other vertical line up here meant divides, such that A times G, say, equals G times A for every other element, little g, in capital G. Okay, either of these for my students would be an okay answer, or they could write both if they wanted to. They should be able to write both. You should be able to write both. On to page 2. One more definition, then we get into some true-false questions. Let G and G bar be groups. Define the definition, what it means for a function phi, say, whose domain is G and whose codomain is G bar, to be what's called an isomorphism. Not a homomorphism. Galilean's book saves homomorphisms for a few chapters after isomorphisms. Okay? Isomorphism definition includes more conditions than homomorphism, but in a sense it's a bit more natural / easy to deal with, and that's why Galilean does it earlier. What does it mean for such a function to be an isomorphism? First of all, it means phi is 1-to-1. In other words, it maps distinct inputs to distinct outputs. You could say if G1 does not equal G2, these are both elements of G. This is not something that you necessarily have to write. You could just say it's 1-to-1, but I'm trying to explain what 1-to-1 means. Then phi of G1 is not equal to phi of G2. Said another way, you could write down the contrapositive of this if-then statement. You could say if phi of G1 equals phi of G2, then G1 equals G2. Again, for my students, I wouldn't require them to write this. They could just say phi is 1-to-1. But for extra emphasis, I'm going ahead and writing what 1-to-1 means in this context here. 2, phi is onto. It'd be fine for them to write that, but let me go ahead and explain what that means. It means for any given, let's call it little g bar, in capital G bar, and it doesn't matter what little g bar is in capital G bar, that's the point in fact, then there exists a little g in capital G that gets mapped to G bar, such that phi of G equals G bar. Okay? Alternative word for one-to-one means is injective. Alternative word for onto is surjective. You could combine these things and say phi is what's called bijective. Maybe your teacher does that. And a third property that is a property shared with homomorphisms is that phi is operation preserving. Phi is operation preserving, or OP for short. And it would be fine for my students to just write that. But you can also write, this means phi of G1 times G2 is phi of G1 times phi of G2 for all G1 comma G2 in capital G. And maybe I'd want to also emphasize to my students that they should be able to write that down, define what operation preserving means, and then they'd actually have to write that. Okay? These are the three conditions to be an isomorphism. What does isomorphism mean? What does it imply? It means that the group structure of these two groups, G and G bar, when there is such an isomorphism, is essentially the same. An algebraist essentially can't tell the difference, you might say, between G and G bar. They act the same algebraically. And this operation preserving property plus the one-to-one and onto effects are the key to making sure that that is true. Bunch of true-false questions. First one. If G is cyclic, then G is abelian. I haven't said what cyclic means yet. I have said abelian a few minutes ago. It means it's commutative. Every element commutes with every other element. It means also the center, Z of G, is equal to G. But what does cyclic mean? Cyclic means G is generated by some element. G equals, what's this notation? This is the notation for the cyclic subgroup of G generated by A. Now, if you haven't gone far enough in your abstract algebra to know what that means, then this question wouldn't make sense. This is the set of all powers of A, as that power n ranges over the integers. And it is a fundamental fact that cyclic groups are abelian. This is true. I'm not going to fully prove that, but let me give you an intuition here. If you've got two arbitrary elements of G, a cyclic group, call them A to the n power and A to the m power, it turns out you can prove a property of exponents. You can write this as A to the n plus m power. N and m are integers here. A is an element of the group. Integer addition is commutative. I could write this as A to the m plus n power. I can switch around the m and the n. And then that can be written by a property of exponents as A to the m times A to the n. And there we have it. A to the n times A to the m equals A to the m times A to the n. That's the essential reason. I'm not writing it as a proof. I'm not writing sentences. But this is true. The next question is the converse of question 7. If G is abelian, then it's cyclic. Okay? That's not something that's completely obviously true or false right away until you have some experience with this. The answer is false. Just because elements commute with each other, all elements, doesn't mean that the group is generated by some element. It doesn't mean every element in the group is the power of some element. What you really need to know this is false is an example. And there are lots of examples out there. Perhaps one of the simplest ones is called U8. This stands for what's called the group of units modulo 8. As a set, it's all the positive integers, bigger than 0, and less than 8, that are relatively prime to 8. There's that word, relatively prime. 8 is 2 cubed, so we're looking for all the positive integers less than 8 that are odd. 1, 3, 5, and 7. And the group operation here is multiplication mod 8. briefly explain what that means in a second here. None of these elements generates U8. 1 squared is not a generator because 1 squared, or 1 is not a generator because 1 squared, for example, is 1. And 1 cubed is 1, and 1 to the 4th is 1, etc. Including negative powers. 1 to the negative 1 means the inverse of 1, but it's itself. 1 to any power in this group is itself, is 1. So 1 is not a generator. 3 is not a generator. 3 squared, of course, in the regular integers is 9, but mod 8, that's equivalent to 1 mod 8. 3 squared is 1, and that means 3 cubed is back to 3, and 3 to the 4th is back to 1, and 3 to the 5th is back to 3, etc. And you're not ever going to get 5 and 7 as powers of 3 when you do mod 8 arithmetic. So 3 is not a generator. 5 and 7 are not generators either. 5 squared is 25. Mod 8, divide by 8 and find the remainder. I forgot to mention what mod means. That's equivalent to 1 mod 8. 25 divided by 8 has a remainder of 1. And 7 squared is 49 is equivalent to 1 mod 8 as well. Okay? So none of these elements, 1, 3, 5, or 7, generate G, this U8. It's not cyclic, but it is abelian. 3 times 5 is 15. Mod 8 is 7. That's the same as 5 times 3. Same with the other products that you can form. This is abelian, but not cyclic, so this is therefore false. Things I'm assuming you're knowing here. So I'm assuming you have some experience with the basics of group theory. Number 9. The dihedral group D3 is cyclic. D3 stands for symmetries of an equilateral triangle. Pretend this is an equilateral triangle. Symmetries of an equilateral triangle consist of certain rigid motions you can do with this triangle that, for example, rotation by 120 degrees or rotation by 240 degrees that make it look the same. You can also just leave it as it is. You can also reflect about lines perpendicular to the sides. You got to pretend this is equilateral. It doesn't look equilateral. You can also do reflections about lines perpendicular to each side going through the midpoint of each side. There's really 6 elements in this group. They are functions, really, and the group operation is function composition. When you compose rotations and reflections, you get a reflection. When you compose any 2 rotations, you get some other rotation. Turns out this is false. It's not cyclic. Given any rotation or reflection, you cannot generate all the other elements in D3 by finding powers of that given element. Powers meaning with respect to composition. That's something to know. Can it be reasoned out? Well, yeah, if you do a lot of work. Perhaps the quickest way to see that it's not cyclic is to associate the vertices of the triangle with numbers, say 1, 2, 3, and think about D3 as being, well, I'm going to go ahead and say it, isomorphic to S3, which is called the symmetric group on 3 objects, whose elements are all what are called permutations of those 3 objects, rearrangements. They're really functions. These are isomorphic. For example, a rotation of this triangle by 120 degrees permutes 1, 2, and 3. 1 gets mapped to 2, 2 gets mapped to 3, and 3 gets mapped back to 1. In cycle notation in S3, that particular function is represented this way as a cycle 1, 2, 3, emphasizing, and you need to understand this, this means 1 gets mapped to 2, 2 gets mapped to 3, and then you go backwards, 3 gets mapped back to the beginning at 1. That would be an example of a rotation by 120 degrees represented as a permutation. This symbol really represents a function. An example of reflection is about the vertical line here, mapping 1 and 3 to each other and keeping 2 fixed. Let's call this alpha, and the other one beta, swapping 1 and 3 but keeping 2 fixed. 1 gets mapped to 3 and 3 gets mapped to 1. You don't see the number 2 in there. It's assumed that 2 gets mapped to itself. I claim alpha times beta, or alpha compose beta, is not equal to beta compose alpha. Alpha compose beta, think about function composition here. You got to work from right to left as you compose these functions. What does that do? Well, when you apply this function, 1 gets mapped to 3, but then when you apply this function, 3 gets mapped back to 1, ultimately meaning in the composition that 1 gets mapped to itself. How about 2? Where does it get mapped to? Well, this first function on the right maps 2 to itself, but then this one maps 2 to 3. So ultimately, 2 gets mapped to 3. How about 3? This function maps 3 to 1, but then this function maps 1 to 2. So 3 gets mapped to 2. You can write this in cycle notation as the permutation 2, 3. On the other hand, if I do it the other way around, what we're going to show here is that this group is not abelian, and by this fact that would actually mean that it's not cyclic. If I do it in this order, I claim I get something different. 1 gets mapped to 2 here, and then 2 gets mapped to itself, so ultimately 1 gets mapped to 2. 2 gets mapped to 3 here, and then 3 gets mapped back to 1, so ultimately 2 gets mapped to 1. And 3 gets mapped to itself. First it gets mapped to 1, and then it gets mapped back to itself when you compose these. And these are not equal. Not equal. So alpha beta does not equal beta alpha. This group S3, which is isomorphic to D3, is not abelian, and therefore by the contrapositive of this statement, which is a true statement, it's also not cyclic. But it's probably quickest to just know this. Number 10. There exist integers s and t such that 4s plus 6t equals 1. This is related to something called the GCD, the linear combination theorem. Such integers s and t would exist if the numbers, in this case 4 and 6, were relatively prime, if their GCD was 1. But wait a minute, 4 and 6 are not relatively prime. The GCD of 4 and 6, the greatest common divisor, is the largest positive integer that divides evenly both into 4 and 6, and that is 2, not 1. These are not relatively prime. And it also turns out that means there's no way this can be done. There are no integers s and t that will make this true. This is false. Number 11. If A is a group element whose order is 6, then a to the negative 8 power equals a to the 4th power. What does order of an element being 6 mean? It means 6 is the smallest positive power of A that gets you back to the identity. 6 is the smallest, and it is important to say, emphasize it's the smallest, positive integer such that when you raise it to that power, you get the identity element, such that, well, let's call it an n. A to the n equals the identity. Okay, that's the assumption we're making here. Is this true? The answer is yes. Why? Well, this equation is equivalent to saying, if you multiply both sides by a to the 8th, e equals a to the 12th. A to the 4th times a to the 8th would equal a to the 12th. 4 plus 8 is 12. And this doesn't mean a has order 12. However, if a has order 6, a to the 6th equals e. That'll mean a to the 12th also equals e, because a to the 12th, well, is a to the 6th times itself. For example, e times e is e. Okay? Could also draw like a cycle diagram to help you see this, where raising a to positive powers goes counterclockwise and raising a to the negative powers goes clockwise. And in either case, you would end up at the same spot, whether you go counterclockwise by 4 turns, 4 steps, or clockwise by 8 steps. This is true. Number 12. The permutations 1, 3, and 2, 4, these are like the permutations I talked about up here, right there, commute. That's true because these are cycles that are what are called disjoint, and disjoint cycles commute. And they commute essentially by definition of what the notation means. Whether you look at it this way or this way, ultimately everything gets mapped to the same thing in both cases. 1 gets mapped to 3, 3 gets mapped to 1, 2 gets mapped to 4, 4 gets mapped to 2. Either way you think about it. Again, working right to left. This is true. If the permutations are not disjoint, disjoint means they have no numbers in common in the cycle notation. If they're not disjoint, they don't necessarily commute, as we saw up here. Okay? These two permutations are not disjoint. They have 1 and 3 in common in the symbols. True or false, the permutation 1, 2, 3, 4, 1 gets mapped to 2, 2 gets mapped to 3, 3 gets mapped to 4, 4 gets mapped back to 1, is what's called an even permutation. Is that true or false? You might think it's even because there's an even number of numbers in this cycle, but that actually means it's false. It means as a permutation, it's actually what's called an odd permutation. What does that mean? It means you can write it as an odd number of 2 cycles. The definition of an even permutation is you can write it as an even number of 2 cycles. The definition of an odd permutation is you can write it as an odd number of 2 cycles. And those two categories are what's called mutually exclusive. An even permutation can never be an odd permutation and vice versa. And through a little trickery, you can write this as a product of permutations like this. That's just a trick to know. It's worth knowing. This 4 cycle can be written as a product of 3 2 cycles, an odd number of 2 cycles, which is why this is false. These are not disjoint 2 cycles. They don't commute, but you can write it this way. Double check it. 1 gets mapped to 2 here, 2 gets mapped to itself, 2 gets mapped to itself, so ultimately 1 gets mapped to 2. What does 2 get mapped to? Well, here it gets mapped to 1, but then here it gets mapped back to 3, and then 3 gets mapped to itself, so ultimately 2 gets mapped to 3. 3 ultimately gets mapped to 4, and 4 ultimately gets mapped to 1 as you work right to left through this composition. 14, multiple choice. How many elements are there of order 2 in S4? What is S4? It's the group of all permutations on 4 objects. S3 was the group of all permutations on 3 objects, the 3 vertices for the equilateral triangle. This is S4 is the group of all permutations on 4 objects, which you can take to be, say, the numbers 1, 2, 3, 4. This is not a group here. This is just a set of 4 objects. S4 is a group of permutations, functions that permute these objects, one-to-one and onto functions that can be composed. The group operation is function composition. How many of these elements have order 2, where 2 then is the least positive integer, such that when you raise the elements to that power, you get the identity? Well, what is the identity element in S4? The identity element, often written as an epsilon for these permutation groups, is the element that maps each number to itself. In cycle notation, it's traditional to just write it like that, or like this, or like this, or like this, emphasizing it's understood that this means everything gets mapped to itself. Certainly when you write it like this, 1 gets mapped to itself, and it's understood 2 gets mapped to 2, 3 gets mapped to 3, 4 gets mapped to 4. How can you have an element of order 4 in S4? There's 2 ways it can happen. It could either be a 2 cycle, AB, where A and B are these numbers 1 through 4, and they're different numbers if I'm writing it like this, or as a product of 2 disjoint 2 cycles. Those are the ways to get elements of order 2 in S4. Okay? There are also elements of order 3, and there are also elements of order 4, but we're not talking about those kinds of elements in S4. So how many elements are there of this form? Well, you've got 4 choices for A, and you want these numbers to be different, so then you're left with 3 choices for B. However, 4 times 3, 12, is not the number of these things that are distinct, because you can write cycles in various forms. A, B, or let's use particular numbers. For example, 1, 3 is the same as 3, 1. You don't have to put the smaller numbers first. This is saying 1 gets mapped to 3 and 3 gets mapped back to 1, but this is saying the same thing. It's not a unique way to write these things. In fact, with 3 cycles, if you have 1, 2, 3, say, You can also write that as 2, 3, 1, and you can also write that as 3, 1, 2. Those are 3 different ways to write those 3 cycles. This is just a separate comment here. So because of that, you have to divide by 2, because for each one of these 2 cycles, there's 2 ways to write it. 12 over 2 is 6. That's the total number of 2 cycles, and they all do have order 2. This is the product of disjoint 2 cycles. 2 disjoint 2 cycles. How many of these are there total? There's 4 choices for A, 3 choices for B, but again, each one like this can be written in 2 ways. Here, you're left with 2 choices for C. You want all these numbers to be distinct, and 1 choice for D, but again, there's 2 ways to do that. And because these cycles are disjoint, you could write it in the other order. So that ultimately means you can divide all this by 2 again. This ultimately becomes 6 times 1 divided by 2. 6 divided by 2 is 3. The answer then is 6 plus 3, or 9. There are 9 2 cycles in S4. The answer is B. Okay? Kind of tricky. Definitely need some practice if you're going to get good at that kind of problem. Now we're on to some computational problems. 15 says, consider the cyclic group G equals Z24. What's Z24? Well, its elements consist of all the non-negative integers less than 24, starting with 0, 1, 2, 3, etc., going up through 23. And the group operation is actually addition, not multiplication, mod 24. And we do use a plus sign to represent the addition, not a times, and not just putting the numbers next to each other. This is a cyclic group. Every element of this can be generated by certain elements of the group, not necessarily all the elements. Under addition, which means instead of powers, you really have like repeated addition. You really, in a sense, have multiples. For example, 1 is a generator. Because, well, 1 is itself. 1 plus 1 is 2. 1 plus 1 plus 1 is 3. 1 plus 1 plus 1 plus 1 is 4, etc. The group operation is addition. Ultimately, if you add 1 to itself 23 times, you get 23. 1 has order 24 if you add 1 to itself 24 times, and then mod by 24, find the remainder when you divide by 24. 24 divided by 24 is 1, remainder 0. That means you get back to 0. You're modding by 24. 1 is a generator. Can I think of another generator? It turns out that 5 is a generator, and there are more. Why is 5 a generator? Well, if you add 5 to itself over and over again, initially you get 5, then 10, then 15, then 20, then not 25, but 1. 25 mod 24 is 1. Then add 5 again, you get 6, then 11, then 16, then 21, then 26 mod 24 is 2. Right? 26 divided by 24 is a quotient of 1 and a remainder of 2. 26 minus 24 is 2. It's divisible by 2. Then 7, etc. I'm off the paper there. I hope it makes sense that you are going to get every element in G here ultimately. So 5 is the generator. In fact, you should know a more general fact. A number in here is going to be a generator if it's relatively prime to 24. 24 is 2 cubed times 3. So we're looking for all the numbers between 0 and 23 that are not even and also not multiples of 3. The generators of G as a set, not as a group, but as a set, consist of 1, 5, 7, right? I don't want any even numbers. I also don't want any multiples of 3. I need to skip over 9, go to 11, then 13, skip over 15 to 17, then 19, skip over 21 to 23. Right? 1, 2, 3, 4, 5, 6, 7, 8 generators in Z24. When you add any one of these numbers to themselves over and over again, you generate all the numbers in Z24. Is this collection of numbers the same as the elements of U24, the group of units under multiplication modulo 24? You might be wondering, why am I calling them units? That's related to something that comes later. The answer is yes, okay? Because by definition, the elements of U24 are the positive integers less than 24 that are relatively prime to 24. Just like U8 consisted of 1, 3, 5, and 7. 1, 3, 5, and 7 were all relatively prime to 8. Under multiplication. And these as elements are the elements of U24. U24, the operation, is multiplication mod 24. It is a different group than Z24. They have a different number of elements and a different operation. And because they have a different number of elements, you could also automatically say they're not isomorphic. Part C, what is the value of, what is this? Is that an isomorphism applied to 24? No. I say phi is the Euler phi function, or phi if you prefer. That's part C. By definition, phi of 24, the Euler totient phi function of the number 24, is the number of positive integers less than 24 that are relatively prime to 24. That's the number of generators. That's 8. Okay? There's actually a formula for finding values of the Euler phi function, but we're trying to keep it basic here and just describe it as being, again, the number of positive integers less than 24 that are relatively prime to 24. And based on the answer in A, and there's 8 of those numbers, this has got to be 8. 16. This is a similar kind of problem, but with different emphases. Let A be a group element whose order is 60. So 60 is the smallest positive integer, giving A to that power equaling E, the identity element, which, by the way, in U24, the identity element is 1 because the operation is multiplication. In Z24, the identity is 0 because the operation is addition. Part A, what are the possible orders of all subgroups of the cyclic group generated by A? A could be an element in some other group, and that other bigger group might not be cyclic. But you always can still consider what's called the cyclic subgroup of that given group. As a set, this is all powers of A in the abstract, as those powers range over the integers. And it is a subgroup of some bigger group, perhaps, or maybe it equals the whole bigger group. So then it's not really bigger. But this itself is a cyclic group, and its order in terms of its number of elements, if A has order 60, is equal to 60. The elements of this start with really A to the 0 power, which is the identity, then A to the first, then A squared, then A cubed, A to the 59th, A to the 60th would be back to E, and then it would cycle again. There's 60 elements here, A to the 0th power through A to the 59th power, and these are all distinct elements. It's a group of order 60. What are the possible orders of subgroups of this? You could answer that by something called Lagrange's theorem. However, Lagrange's theorem is not in chapters 0 through 6 of Gallien's book, and so I don't cover it yet. Instead, there's something called the fundamental theorem of cyclic groups. And again, A might be in a bigger group that's not cyclic, but it still generates a cyclic subgroup. And the fundamental theorem of cyclic groups says that when you know the order of your cyclic group, you can actually say more than what the question is asking. You can actually say there is exactly one subgroup for each divisor, each positive divisor of, in this case, 60. 60 is 5 times 12, 12 is 3 times 4. 60 can be factored as 2 squared times 3 times 5. That is its prime factorization. And that helps you figure out the possible orders. You want to write down all possible positive integer divisors of 60, and that'll help you to know the prime factorization. Or you could sort of stack up the divisors like this. 1 times 60 is 60, so we can have 1 or 60 as possible orders of subgroups. This would be called the trivial subgroup containing just E. That would be your one element. 60 would represent the entire group generated by A itself. Other divisors include 2, 3, 4, etc. 2 times 30 is 60, 3 times 20 is 60, 4 times 15 is 60. 5 would go with 12, 6 would go with 10, and that would be it. There are 12 positive integer divisors of 60, these 12 numbers. These are then, by the fundamental theorem of cyclic groups, the possible orders of all the subgroups of this cyclic group. And moreover, you can also say there is exactly one subgroup of each of these orders. B. List the elements of the cyclic subgroup generated by a to the 12th power. Well, there is a to the 12th power to the 0th power. E, the identity, is going to be in there. A to the 12th will be in there. N other powers of a to the 12th. A to the 12th squared is a to the 24th, property of exponents. A to the 12th cubed is a to the 36th. A to the 12th to the 4th power is a to the 48th. A to the 12th to the 5th power is a to the 60, but a to the 60, because A itself has order 60, is back to E. So in fact, that's the last element. This group, this cyclic group, has order 5. 1, 2, 3, 4, 5 elements in it. And that also means, for part C, the order of the element a to the 12th is 5. You don't have to list that out to see that. You could also be thinking about the fact that a to the 12th to the 5th, 5 would be the smallest positive power of a to the 12th. That would get you back to the identity, because A itself has order 60. This also can be found by doing the order of the bigger cyclic group itself, 60, divided by the GCD of 60 and this power 12. That GCD is 12, and 60 divided by 12 is 5. And that fact will help us for part D. What is the order of a to the 45th? We could try to figure it out by listing out the elements of the cyclic subgroup generated by a to the 45th. But we can also use the same kind of calculation here. We can take the order of the bigger group, 60, divided by the GCD of 60 and this power, 45. What's the greatest common divisor or greatest common factor of 60 and 45? Think a little bit, it would be 15. The answer is 4. What would the elements of the cyclic subgroup generated by a to the 45th be? They would include E, a to the 45th, a to the 90th power mod by 60. That's going to be the same as a to the 30th power. A to the 135th power mod by 60. That's going to be the same as a to the 15th power. And then a to the 180th power would be E, because 180 divided by 60 has a remainder of 0. Yeah, those would be the 4 elements. Not asked for, but if you wanted to know it, that's what it would be. Another page with a couple more calculation kind of problems. After this page come the proofs. More permutations. Consider the following permutations given the cycle notation. Alpha is this, beta is this, gamma is that. That's a gamma there. Part A, write the inverse of beta in cycle notation. Well, it's an inverse function. If beta maps, as we see here, 3 to 4, then beta inverse is going to map 4 back to 3. Beta maps 4 to 7, so beta inverse will map 7 back to 4. Beta maps 7 to 6, so beta inverse will map 6 back to 7. Beta maps 6 to 3, so beta inverse will map 3 back to 6. What you can do for beta inverse is just write these numbers in the opposite order. 6, 7, 4, 3. And again, this is not a unique way to write it. We could also write it as 7, 4, 3, 6, or 4, 3, 6, 7, or which one's left? 3, 6, 7, 4. These all represent the same function, the same permutation. Part B, write beta squared and beta times gamma as cycles or products of disjoint cycles. Beta squared, there's beta, composing this function with itself. Go right to left. 3 gets mapped to 4, but then 4 gets mapped to 7, so ultimately 3 gets mapped to 7. 7 gets mapped to 6, but then 6 gets mapped back to 3, so 7 ultimately gets mapped to 3. There's no 1, 2, or 5 in here, so they stay fixed. What about 6 and 7? Or, excuse me, what about 4 and 6 is what I mean. 4 gets mapped to 7 here, but then 7 gets mapped to 6, so ultimately 4 gets mapped to 6. 6 gets mapped to 3, then that gets mapped to 4, so ultimately 6 gets mapped to 4. And that does it. And this is disjoint, so these commute. I could also write the answer as 4, 6, 3, 7. And I also could write it as 7, 3, 6, 4, or blah, blah, blah. Okay, there's lots of different ways to write this. What about beta times gamma, really beta compose gamma? Beta compose gamma, 3, 4, 7, 6 composed with the cycle 2, 7. 1 will stay fixed under the composition. There's no 1 in either one of these, as will 5. How about 2? 2 first gets mapped to 7, but then 7 gets mapped to 6, so ultimately 2 gets mapped to 6. 6 gets mapped to itself under the first one here, but then to 3 under this one, so ultimately 6 gets mapped to 3 under the composition. Ignore that. What about 3? 3 gets mapped to itself, then get to 4. What about 4? 4 gets mapped to itself, then to 7. 7 here gets mapped to 2, but then 2 stays fixed, so ultimately 7 gets mapped to 2. So that would be one form of the answer. Again, ignore that part there. That's a cycle. Okay, we don't have to try to write it as a product of disjoint cycles. This is a product of disjoint cycles. This is just one plain cycle. C, compute the order of alpha, beta, and say what factor you're using. And so evidently there's some fact that I haven't mentioned yet that could be used instead of actually computing the order of alpha, beta by doing powers of alpha, beta, and you definitely want to use this fact. Notice alpha and beta are disjoint cycles. None of their numbers are in common. That's enough to say that the order of alpha, beta, because of that, is the least common multiple of the order of alpha and the order of beta. Now the order of alpha, being a 3 cycle, is 3. Alpha squared, to help you believe this here, alpha squared, what does that do? Well, alpha maps 1 to 2, but then 2 to 5, so ultimately alpha squared maps 1 to 5. Alpha maps 5 to 1, but then maps 1 to 2, so ultimately 5 gets mapped to 2. And you can check that 2 gets mapped to 1. So alpha squared is not the identity, but alpha cubed is. Okay, I'll let you check that out. I won't calculate it here. Alpha cubed is the identity. It maps everything to itself. A 3 cycle by itself has order 3. Beta is a 4 cycle. It's got order 4. It's not an odd permutation. Excuse me, it's not an even permutation, it's an odd permutation. And by the way, 3 cycles are even permutations. But it does have order 4. And what's the least common multiple of 3 and 4? It's 12. And this is definitely the way to go for part C here. Because if we were to compute alpha, beta, which we can certainly do, and then raise it to powers, it would only be until we got to the 12th power that we would get back to the identity. That would take a long time. '18 is about something called the stabilizer. of an element under a group of permutations. In Gallien's book, stabilizers are not studied in detail until I believe it's chapter 7, which, we're only going through chapter 6 here. However, I'm describing what a stabilizer is in this problem. And what we're ultimately trying to do here is a proof. Actually, this is our first proof, not the next page. That the stabilizer of an element of a permutation group on a set is a subgroup. This does not mean less than or equal to. It means what's called subgroup. It's a group within a group under the same operation, the same binary operation. Let's get a little more context. G is a group of permutations on a set X. X could actually be an infinite set, for all you know. Okay? Permutations on a set are one-to-one and onto functions from the set to itself. S3, for example, symmetric group on 3 objects, is the collection of all one-to-one and onto functions from the set 1, 2, 3 to itself, permuting the elements, where the group operation is function composition. X is any non-empty set here. Let A be an element of X and define the stabilizer of A by this formula here. It's the set of all permutations in G, one-to-one and onto functions from X to itself. A is an element of X. That map A to itself, that keep A fixed. And then in part B, we'll think about an example. But part A is our proof, our first proof. And this is an easy enough proof to use something called the one-step subgroup test. Now, a little bit of truth in advertising. The one-step subgroup test is actually 2 steps. So the first step is thought of as a trivial 0th step, you might say. There's also a 2-step subgroup test, which is really 3 steps, where the 0th step is trivial enough to just call it the 2-step subgroup test. The first step, or 0th step, is to verify that this set you're trying to prove is a subgroup of G is non-empty. And that usually is pretty easy. In this case, it's easy because epsilon, the identity element of G, definitely maps everything to itself. In fact, by definition, that's what epsilon is. Since epsilon of A maps A to A is something specific, but I could say this is true for any element of X. Epsilon fixes A. That means epsilon is in the stabilizer of A. So the stabilizer is non-empty. The 0th step is to show that the given thing you're trying to prove is a subgroup of the given group is a non-empty set. And that often is a pretty easy thing to do. This is by definition of this function epsilon. Not using cycle notation here. Again, X could be an infinite set. And when you're doing permutations, your elements that are being permuted don't have to be numbers. They could be geometric objects. But epsilon is a function. A is an element of X. What's next in this one-step subgroup test? That's the 0th step. What's the first step, which will be the final step? Let alpha and beta be arbitrary elements of the stabilizer. To finish the one-step subgroup test, we must show that alpha composed beta inverse is also an element of the stabilizer. And if we can do that, we'll be done. And what does that mean? It means when you plug A into this function composition, it maps it to itself. The output is also A. But we need to use our assumption here. Alpha and beta stabilize A. They map A to itself. And since beta maps A to itself, beta inverse also does. We're essentially done. It's a pretty easy thing to do once you know what to do. Since alpha is in the stabilizer, we can say alpha of A equals A. Since beta is in the stabilizer of A, beta of A will equal A as well. So by definition of inverse function, beta inverse of A also equals A. If beta maps A to itself, so will beta inverse map A to itself. Therefore, three dots means therefore, alpha beta inverse of A. Well, first of all, that's alpha of beta inverse of A, but beta inverse of A is A, and alpha of A is A. We're done. Therefore, alpha beta inverse is in the stabilizer of A. So we are done by the one-step subgroup test. Show the proposed subgroup is non-empty. And show that given any two elements of the proposed subgroup, call them alpha and beta, show this alpha times beta inverse is also in that given set that you're trying to show is a subgroup. Notice this is definitely a subset of G. That was probably worth mentioning as well. These elements alpha are all in G. Part B, let X be this set of three numbers and G be S3, symmetric group on three objects. Write down the elements in the stabilizer of 2 as cycles or products of disjoint cycles. G is S3. Turns out it's got 3 factorial elements, 6 elements. S4 has 4 factorial, 24 elements. S5 has 5 factorial, 120 elements. We could represent these elements as, well, there's epsilon, which we can write in cycle notation like that, because X here is this set 1, 2, 3. Another permutation is 1, 2. 1 maps to 2, 2 maps to 1, 3 maps to itself. Another one is 1, 3. Another one is 2, 3. Those are all cycles. And then there's 2 more elements that are also cycles. 1, 2, 3, and 1, 3, 2. You could write that one as 2, 3, 1 or 3, 1, 2. You could write this one as 3, 2, 1 or 2, 1, 3. Which of these fix 2, stabilize 2, map 2 to itself? Certainly the identity does, and the only other one that does is this one. All the other ones map 2 to something other than itself. The stabilizer of 2 consists of just epsilon and the cycle 1, 3. And that is a subgroup of G. Okay? A 2-element subgroup of G. G has order 6, this subgroup has order 2. Two more pages of proofs, actually just 3 more proofs. This one is about isomorphisms, and we're going to need mathematical induction. G and G bar are groups. Phi mapping G to G bar is an isomorphism, so 1-to-1 onto an operation preserving. Carefully use induction to prove that given an element A in G, phi of A to the n equals phi of A all to the n power for all positive integers n. Essentially, the operation preserving property gets carried over to powers of the input element. This is actually a limited fact we're proving. It's actually true even when n is a negative integer. It's also true if n is 0. But to keep it simple for induction, we're just doing it for all positive integers. First, there's the inductive step. Show the thing you want to prove. This thing is true for n equals 1 in this case. That's usually pretty easy, and that is here. Note that phi of A to the first is phi of A, because A to the first is A, is phi of A quantity to the first, because phi of A quantity to the first is phi of A. Raising something to the first power, by definition, gives you itself. Therefore, the inductive step holds. I could write, therefore, the statement is true when n is 1, the statement that we're trying to prove here. Actually, that's the base case. Sorry, that's the base step. The inductive step is to assume phi of A to the n equals phi of A quantity to the n for some integer n greater than 0, some positive integer. That's the base step or base case. This is the inductive step. We must show that the same equation holds for the next value of the exponent, which would be n plus 1. That's what we must show. Now, by saying we must show, I haven't actually shown it. I'm just writing down what I'm trying to show. But it's fairly easy. You need to use your inductive assumption, inductive step here. You need to use that assumption, otherwise why assume it? And we also need to use the fact that phi is an isomorphism, so it is operation preserving. This follows from the following calculation. Which holds since phi is operation preserving property and by our assumption. When doing an inductive proof, you always have to use the assumption in the inductive step. Here are the steps. Phi of a to the n plus 1. By definition, that's phi of a to the n times a. That's the way to try to connect this to the inductive hypothesis. Phi is operation preserving, so this is phi of a to the n times phi of a. That's the OP part. This first step is really the definition of, well, it's a property of exponents. But we need to use the inductive hypothesis that this is true. Use it now on this. This is the same as phi of a to the nth power times phi of a. That's the assumption, the inductive hypothesis. And then by property of exponents, this is the same as add the two exponents, phi of a to the n plus 1. And that means we're done. It's good to write maybe one more line. Therefore, by induction, or by the principle of mathematical induction, and I just dropped my pen there. Sorry. We can say phi of a to the n equals phi of a to the nth power for all positive integers n. Emphasis on the for all, not just this particular n. In fact, it might have been good to use a different letter up here other than n. This is like a particular n up here, and this is for all n down here in your conclusion. If my students, if you use n in both spots, I will not mark it wrong. But ideally, it'd be good to use some other letter like k or something, or m up here, and use the n down there. 20. G and G bar are groups. K is a subgroup of G, and phi is an isomorphism from G to G bar. Prove that the direct image of K under phi, this set right here, is a subgroup of G bar. Okay, the subgroup test again. You may assume we know what we proved partially in number 19. This equation, it's actually true again, even if n is negative or 0. And we'll actually need it when n is negative if we want to use the one-step subgroup test, which we do want to use. Visually, you can imagine G as being like a blob here and G bar as being a blob here. And phi is mapping G to G bar, and K is some subgroup of G, not just a subset, but also a subgroup under the same operation. And so it would also include, for example, the identity element. Phi of K, the direct image of K under phi, is the set of all possible outputs of phi when little k ranges over capital K. It's definitely some subset of G bar. In fact, it's a non-empty set because we know E is in K. So it will contain phi of E. Since E is in K, because K is a subgroup of G, it's got to have the identity element. It's a subset, but also a group under the same operation. The identity of G is going to be the same as the identity of K. Phi of E is in phi of K, so phi of K is non-empty. And realize when I say phi of K, I'm not literally plugging K into phi, because K is a set and not an element of G. I go ahead and say phi of K, but it means this. It's a set of all possible outputs as little k ranges over capital K. One-step subgroup test. Now assume you've got two elements in this direct image phi of K. Call them, say, C and D, maybe. We must show CD inverse is in the direct image. Okay? And then we can say by the one-step subgroup test, that'll mean this direct image is a subgroup of G bar. It is certainly a subset of G bar, because its elements are phi of K, and phi of K elements are in G bar. How do you do this? We must have to use this assumption. That's probably the first thing to try. Since C and D are in the direct image, there exists, say, an A and a B in K such that C equals phi of A and D equals phi of B. That's what it means for C and D to be in that direct image. To show C D inverse is in the direct image, we've got to find something in K that gets mapped to C times D inverse. How about A times B inverse? It's worth a try. And it does work. Since phi is OP, being an isomorphism, phi of A B inverse is phi of A times phi of B inverse. That's the OP part. And because of this, which is true even when n is -1, phi of B inverse is phi of B inverse, the inverse of phi of B. Phi of A is C, phi of B is D. We have just verified that CD is the image of something in K. It is in the direct image. It's in phi of capital K. This again is the OP part. This is the property of exponents, you might say. Well, it's this property, which you could call property of exponents, I guess, if you wanted to, but it's not the usual kind. And this is assumptions. We were assuming C and D were in phi of K. Therefore, CD inverse is in phi of K. Therefore, phi of K is a subgroup of G bar by the one-step subgroup test. And we're done. QED, I forgot to mention QED. Or if you believe in God, praise the Lord. We're done. Yay. One more problem. A proof, in part. Define a relation, triple line, triple equal sign, relation on the set of integers z by saying A is related or equivalent to B. This is going to be an equivalence relation if and only if 4 divides A minus B. Part A is to carefully prove that this thing is an equivalence relation on the integers. And part B is to describe or write down the equivalence classes of Z with respect to this equivalence relation. Equivalence relations satisfy 3 properties. Think of it in alphabetical order: reflexive, symmetric, transitive. Reflexive means any element is equivalent to itself. Symmetric means if A is equivalent to B, then B is equivalent to A. And transitive means if A is equivalent to B and B is equivalent to C, then A is equivalent to C. Reflexive property. Is A equivalent to A? Yeah, because 4 divides A minus A. A minus A, which are integers, is 0. And any number divides 0. A minus A equals 0, and 4 divides 0. So A is equivalent to itself. Mod 4, you might say, but I won't say it. Symmetric. I should have said let A be an element of Z to begin with. Let A and B be both elements of Z, and suppose A is related to B, A is equivalent to B. Then, by definition of what this equivalence relation is, that means 4 divides A minus B. We need to show B is equivalent to A. We need to show 4 divides B minus A. Okay. Divides, we're back to number 1. There exists an integer m such that A minus B equals 4m. But then B minus A, these are integers, will equal 4 times negative m. Multiply both sides by negative 1. We know how to deal with integers, where negative m is an integer. By the way, the integers do form a group under addition. Not mod anything, ordinary addition. Therefore, B is equivalent to A. Finally, the transitive property. Let A comma B comma C be in Z with A equivalent to B and B equivalent to C. Then that means 4 divides A minus B. It also means 4 divides B minus C. There exists an m and an n, say, that are integers such that 4 divides A minus B. A minus B is 4m, and B minus C is 4n. Now add these equations. If it's not clear what to do, you got to experiment. And cancel the b's to say A minus C is 4m plus 4n, right? If you add these two equations, A minus B plus B minus C, the b's cancel, and you're left with A minus C. Add 4m and 4n, and that's the same as 4 times, in parentheses, m plus n, where m plus n is an integer because the integers are closed under addition. The integers are a group under addition. Therefore, A is equivalent to C. And these 3 things that I've just proved are enough to say that this relation is an equivalence relation. The one we defined where I used 4 here. The 4 is arbitrary. Could pick 5, 6, 2. Okay, I picked 4. In part so that part B is manageable. Part B, describe or write down the equivalence classes of Z with respect to this equivalence relation. And I'll go ahead and use the special notation for equivalence classes. What's the equivalence class of 0, for example? It's all elements of Z that are equivalent to 0 under this equivalence relation. All elements of Z such that those elements minus 0 is divisible by 4. It'll be an infinite set, and it'll contain negative 8, for example, negative 4, 0, 4, 8, etc. All multiples of 4. I could also write this way or this way, etc. This is the equivalence class, a subset of Z containing all these numbers. And this is standard notation. It does not contain the number 1. What's the equivalence class of 1? All integers such that when you subtract 1 are divisible by 4. That'll include 1 itself. 1 minus 1 is 0, which is divisible by 4. It'll include 5. 5 minus 1 is 4, which is divisible by 4. It'll include 9. 9 minus 1 is 8, which is divisible by 4. 13, etc. 17, 21. It'll also include, careful, not negative 5, but instead negative 3. Negative 3 minus 1 is negative 4, which is divisible by 4. Negative 7, negative 11, etc. Hopefully you see the pattern now. For 2, it'll be 2, 6, 10, 14, etc. And also negative 2, negative 6, negative 10, etc. For 3, it'll include 3, 7, 11, 15, etc. Also negative 1, negative 5, negative 9, etc. And there's no others. There are 4 equivalence classes. The equivalence class containing 4 is the same as the equivalence class containing 0, etc. Those are the equivalence classes. These do form what's called a partition of the integers. They are disjoint. The intersection of any of these 2 of these sets is empty. And their union is all of Z. That's called a partition of Z. And these are called equivalence classes. Thanks for watching.